Okay, let's find the directional derivative of our function f of xy at the point 1, 1 in the direction of the vector that we can form from the points p to q, which is 4, negative 3. So let's look at what the directional derivative is, and we'll do this because this is a slightly different problem. So I'm drawing my coordinate axes. There you go. And if we have our surface, and if we want to find, say, this point xy, we want to find the slope, it's not easy to do so because there's so many different directions we can think about. And one of those directions happens to be x, in the x direction. Another direction happens to be the y direction. Those are the partial derivatives we've seen earlier. But if we want to find it in the direction of some vector v or something like that, we have to essentially use the directional derivative with the gradient dot product with the unit vector, which specifies the direction of that vector, and we ignore the magnitude because it's not important. And so we can do that. We can use that formula, that idea, to figure this problem out. Keep in mind that we are not given a vector, we're given a direction, and we're given a direction through 2 points. We have to find the vector going through those 2 points, and that's going to give us the vector that has the direction. We can find the direction by finding a vector that only has a direction and magnitude of 1 by dividing the vector that we get from the points p to q by the magnitude of that vector, and then dot producting that with the gradient at the point 1, 1. So that's a lot of saying, but let me do stuff now. So we have a derivative in the direction of u. Now you don't know what u is yet, but we'll see what that is. Of f xy. This is just simply equal to the gradient of our function xy dot product with the unit vector. It's a very important formula here. Now let's go ahead and figure out the gradient. That's just the composition of our partial derivatives. The partial derivative with respect to x is just equal to, treating y constant, is 1/2 xy raised to the negative 1/2 power times y, and then with respect to y is 1/2 xy raised to the negative 1/2 power times x. This is y over 2 root xy. Fy is x over 2 root xy. Okay, let's figure out what this is going to be now. This is just going to be y over 2 root xy, comma x over 2 root xy. Okay, let's go ahead and evaluate it at a point 1, 1. So that's just 1 over 2 root 1, comma 1 over 2 root 1, which is going to be 1 over 2, comma 1 over 2. That's our gradient at the point 1, 1. Okay, now let's find the vector u. That's going to be the magnitude. Actually, let me not write that now. It's going to be, first of all, let's find the vector v that goes through those 2 points. So point p, which is 1, 1, and point q, which is 4, negative 3. This is very easy. Just take negative 3 minus 1. And, well, first let's do the x component. So it's going to be 4 minus 1, which is 3, negative 3 minus 1, which is negative 4. That gives you the vector v. It's very simple. And then what we want to do is we want to find u, because we only care about the direction, not the magnitude. We can take our vector v and divide it by its magnitude. Our vector v is 3, negative 4. The magnitude of our vector v is, I think it's 9. I might be wrong. It's not 9, it's 5. So it's the square root of 9 plus 16, which is 5. So this ends up being 3/5 comma negative 4/5. And just to put it all together, we have the directional derivative in the direction of u of f of xy is equal to the gradient, which is up here. We have 1/2, 1/2. Dot product with 3/5 negative 4/5. 1/2 times 3/5 plus 1/2 times negative 4/5 gives you 3/10 plus, well, minus 4/10. Negative 1/10. That is the directional derivative at the point at the point 1, 1 in the direction of the vector b, which we formed from the 2 points p and q. So that's it.